Reciprocal and rational functions. So remember, reciprocal functions are just a special form of rational function where we don't have an x value in our numerator. We just have a number in our numerator, and our x value or our variable ends up in the denominator. So this is the special form of rational functions. So I'm going to kind of be talking about these things synonymously because they're very, very similar. So for both reciprocal functions and rational functions, our parent graph looks like what you see here. We have two hyperbolic curves, one showing up in the top right, one showing up in the bottom left, and we end up with an asymptote happening at the y-axis and another asymptote happening at the x-axis. So we have an asymptote of y equals 0 and another asymptote of x equals 0. So because our axes are our asymptotes, this parent function doesn't actually have any intercepts because we can't cross those axes. When we start moving them around, we'll start to see those intercepts showing up. So when we are transforming a rational function, so a rational function ends up in the form like this. Remember, we only have to deal with linear on linear. So ax plus b being divided by cx plus d. It's the same shape. We still get that hyperbolic curve. But we're going to start making the position different, the shape different, and we might be reflecting it. All of that can be determined by these four values, these four coefficients. So if I'm looking for the y-intercept, the y-intercept occurs when x equals 0. So if I put 0 in for my x values, that causes this to disappear and this to disappear. So my y-intercept just becomes b divided by d. So I take my two constant values and I divide them, and I end up with my y-intercept. When I'm doing the opposite and finding the x-intercept, I need to make y 0. So this time I'm going to put the 0 in for y. If I wanted to solve for x, I need to multiply both sides by this denominator. But if I multiply by 0, that causes that to disappear. So we end up actually just solving to find our x-intercept, ax plus b equals 0. So we get x equals negative b over a. So you'll see these nice things start happening that start simplifying our life a little bit. And you can remember to stop the video anytime if you need to write these notes, because I'm going to keep putting the notes in and then erasing them as I need different values in this function. The vertical asymptote occurs when the denominator equals 0. So you need to take whatever the denominator is, and you need to set that thing equal to 0, because we cannot divide by 0 without creating a massive black hole. And we don't want those in our universe. So we're going to subtract d over and then divide by c. So it always ends up in this same pattern. When we are dealing with our horizontal asymptotes, we end up with, sorry, let me just erase that, the coefficients of our x values. The coefficients of our x values is what creates our horizontal asymptote. So whatever these coefficients are, when we divide them, that becomes our horizontal asymptote. Remember, it might not be written in this order. It can be written as, say, like ax plus b over d plus cx, but you're always just looking for those values in front of the x's. If you can find those values, you can find your horizontal asymptote. So what does that look like with numbers? Well, let's see. So it wants us to sketch the graph of y equals 3x plus 4 over x. When we just have a single denominator like this, we can actually simplify this function to make our life even easier. So this is the same thing as if I wrote 3x over x plus 4 over x. So this first term can be simplified and we can get rid of these x values. So I end up with 3 plus 4 over x. The reason this simplifies our life a little bit is because now we are dealing with a form of a reciprocal function. So this is now a reciprocal function. So if we apply our transformations, if I add something outside a function, that means move my function up 3 places. So my my horizontal asymptote used to be y equals 0. But now I need to move that y value up 3. So my new horizontal asymptote is going to be y equals 3. So my new horizontal asymptote is going to go right through here. We're going to pretend that's a nice straight line at y equals 3. You can see we can get that same thing by dividing our coefficients. If I go 3 divided by 1, I still get that y equals 3. To find my vertical asymptote, I need to take my denominator and set it equal to 0. So my vertical asymptote is just x equals 0. So we still end up with that being the y-axis. So now we need to figure out our intercepts. Well, obviously, we're not going to have a y-intercept because we never cross the y-axis. So we need to find the x-intercept. So we need to take our function and set it equal to 0. So for our x-int, we're going to go 0 equals 3 plus 4 over x. We're going to subtract 3, 4 over x. Play our lovely switcheroo game and get that x equals negative 4 thirds. So we're negative, so we're over here on the negative side, and we're just a little bit bigger than 1, so we can put our dot about there. So this tells me like a hyperbolic curve, I'm going to have 1 down here, making sure I sort of pass through that x-intercept. And then we need to put it over on the other side and have this guy over here. You can see I have my 2 asymptotes labeled, and I have my intercept. When they can't be simplified like this, that's when we need to do all of our work. So last example here. So start with our steps. Let's start with our horizontal asymptote. Horizontal asymptote, we need to find the 2 coefficients of our x and divide them. So y is going to equal 6 over 2. Y is going to equal 3. So we once again have an asymptote at y equals 3. For the vertical asymptote, we need to take our denominator and set that whole thing equal to 0. So we're going to have 2x minus 8 equals 0. 2x equals 8. X equals 4. So now I have a vertical asymptote way over here at x equals 4. So that gives me my 2 asymptotes. Now we need to do the intercepts. So to find the y-int, we need to make x equal 0. Remember, when we make x equal 0, this disappears and this disappears, and we end up with just whatever is our constant functions. So our y-intercept is going to be x is 0, and y is whatever 4 divided by negative 8 is, which is 0 and negative 1 half. So x is 0, y is negative a half, so it's about, yeah, sure, there-ish. when we're dealing with the x-intercept, we need to make y 0. So we're going to make y 0. So we're going to have 0 equals 6x plus 4 over 2x minus 8. So remember, when I multiply the denominator by 0, it just disappears. So we actually only give a crap about the numerator. So we're going to subtract 4. And then we're going to divide by 6. And of course, that can be simplified. So in this case, y is 0 and x is negative 2/3. I said that right and wrote that wrong. Hold on, let me fix that. X is negative 2/3, y is 0. Ah, that looks a whole lot better. So we have 0 and negative 2/3. So we're over here somewhere. And I realize that this dot should be down here somewhere because it's negative. So again, so the reason I could tell that I put that dot in the wrong place is I was trying to draw the hyperbolic curve in my head and it wasn't working. So that told me that I needed to go back and check my work and see where I had made my mistake. And my mistake was that I had put this at positive a half instead of negative a half. So now I can picture in my head how that hyperbolic curve is going to look. It's going to start up here, but kind of by that intercept, or sorry, that asymptote, go through these two intercepts, and then come down here. And then we need to go to the other side and create that other hyperbolic curve. There you go. Two examples, one of a kind of reciprocal function and one of a rational function. Hope this helps.